Hello teacher, hello students. This is a mathematics tutorial series which is organized by Oromia Education Bureau. I am Dr. Garuma Abdisa from Mattu University, and our today's topic is about exponential and logarithmic functions. Exponential and logarithmic functions are so much powerful and useful both academically and technologically that the study of logarithmic functions is very useful. Before I proceed directly to logarithmic functions, let me say a little bit about polynomial and rational functions. Polynomial functions and rational functions are examples of algebraic functions. However, exponential and logarithmic functions are a group of functions which are known as transcendental functions. So both logarithmic and exponential functions are transcendental functions, and we have to keep this in mind. Here is the definition of exponential function. The exponential function f with base a, always logarithmic functions and exponential functions have a certain base that in this generalized model I am simply calling that to be a, is denoted by f of x, which is equal to a to the power x. This is an exponential function where a has to be greater than 0 and a is different from 1, because if a is equal to 1, what happens is 1 to the power of everything becomes 1, and instead of becoming a function, it becomes a constant function which attains every time a single value, which is only 1. So in order to avoid that, we have to restrict 1 from becoming a base, and the base of any exponential function cannot be 1, and it has to be always greater than 0. How do we evaluate exponential functions? For example, in this case you can use for example a scientific calculator or on your mobile phone, because I want you how to prepare a table of value and how to have in your mind what happens when, for example, the base is 2 to the power of x when we substitute x to be minus 3.1, or 2 to the power of minus x when that x is, say, for example, pi or any other number. How do we evaluate those values? It means that, for example, if we have 2 to the power of x and substitute x to be minus 3.1, it becomes 2 to the power of x, where our x is minus 3.1. So this is equal to 2 to the power of minus 3.1. So how do we evaluate this kind of expression? This is equivalent to 1 divided by 2 to the power of positive 3.1. An exponential expression having a negative on as its exponent is equivalent to 1 divided by the exponent now becoming positive. So in general, for example, if you want to write a to the power of some minus x, it is equal to 1 over a to the power of positive x. So it turns out that the number will be small, and it will be in fraction, because 2 to the power of 3 is a larger number. Now it has 0.1. 2 to the power of 3.1 is a larger number, at least a little bit equal to 8. And 1 divided by that will be small, and that's why we see the value being evaluated from a scientific calculator gives us only 0.11 something. So the most important thing I wanted to demonstrate to you here is when the exponent becomes positive or negative, what will be the behavior of the exponential function, not just how to pick them out from your scientific calculator. That doesn't matter a lot. But when the exponent becomes positive and when the exponent becomes negative, what will be equal to the given expression? For example, I still have 2 to the power of minus x, where my x is pi. In this case, it will be equal to 2 to the power of, here is minus x. For x, I have pi, so it will be equal to 2 to the power of pi. Means 2 to the power of about 3.14. So because my expression is 2 to the power of minus x, I'm substituting x to be pi, so it becomes 2 to the power of minus pi, that is 2 to the power of minus 3.14. So that is again equal to 1 divided by 2 to the power of 3.14. 2 to the power of 3.14 will be a number a little bit larger than 8 as we expect, because even if we ignore the 0.14 term, 2 to the power of 3 alone is already 8. 2 to the power of 3 is 8. So 1 divided by a number a little bit larger than 8 will now give us 0.1133147. That is something that you can take from your calculator. But the key point of this lesson is that whenever the exponent becomes negative, what will be the behavior of the exponential function, and when the exponent becomes positive, the exponential functions either increases, its magnitude increases, or when the exponent becomes negative, the exponential function, the equivalent of that exponential function will be 1 over the positive exponent, and it will be reduced. That is something that you can learn out of this. On the other hand, when the base is a fraction, that is, for example, I have 0.6 to the power of x. Now my x is 3 over 2. That is equivalent to 0.6 to the power of 3 half. That is to the power of 3 over 2. It means 0.6 the power 3, and now taken from the square root. This is the same as 0.6 the whole cubed, and the power a half means is like we are taking this again from the square root. That is the way we evaluate this number. And finally, we get 0.464 if you use your calculator. You may wonder why I have brought this and what will be the advantage of dealing with the values of this kind of exponential function is as follows, that once you learn how to find the value of this kind of exponential functions, it will help you to graph. That's why I brought that to a little bit before I talk about graphing a rational function. Suppose we wanted to plot the graph of a rational function y is equal to a to the power of x. And in order to achieve that, what we have to first do is prepare a table of values such as this one, as you see it here on the board. First of all, I write x here, and then, for example, I have two exponential functions. One is 2 to the power x, and another one is 4 to the power x. And if I substitute minus 3, minus 2, minus 1, 0, 1, and 2 for both of them, in a similar way that I told you earlier, for example, if I have 2 to the power of x, if I substitute minus 3, then what I get is 2 to the power of minus 3. 2 to the power of minus 3 means is equal to 1 over 2 to the power of 3. 1 over 2 to the power of 3 means is 1 over 8, and 1 over 8 is the one that you see it here. In a similar way, if you substitute minus 2 instead of x here, 2 to the power of minus 2 is the same as 1 over 2 to the power of 2. That is equal to 1 over 4. So that is 1 over 4 that you see it here. In a similar way, if I substitute minus 1, it will be 2 to the power of minus 1. 2 to the power of minus 1 means is 1 over 2. If I substitute 0, 2 to the power of 0 is 1. Students, every number to the power of 0 is always equal to 1. For example, 100 to the power of 0, or 1 to the power of 0, or 2 to the power of 0, any number to the power of 0 equals 1, and that's why we write 1 there. And if I substitute 1 instead of my function here, 2 to the power of x, 2 to the power of x, now if I substitute 1, it becomes 2 to the power 1. Any number to the power 1 is the number itself, that is 2. If I substitute 2 to the power of 2 is 2 squared, that is equal to 4. And by doing the same thing for the other exponential functions that I have, namely 4 to the power x, if I substitute minus 3, it becomes 4 to the power of minus 3, or 1 over 4 to the power of 3. And 4 to the power of 3 means is 64. So it is 1 over 64. In a similar way, this one is 4 to the power of minus 2. That is 1 over 4 squared. that is 1 over 16. If I substitute minus 1, 4 to the power of minus 1 is 1/4. If I substitute 0 instead of 4 to the power of minus x, with a similar argument that I told you before, any number to the power 0 is 1. And if I substitute 1, 4 to the power 1 is simply 4. And if I substitute 2, 4 squared, that is 16. So the only difference between the upper and the lower is that their bases are different, and consequently their functional values will be also different. So in order to sketch means to plot. To sketch means is to plot the graph of the function. First plot the pointers, means these pointers that you can see them on the board here, that we have prepared a table of values together. And then based on that table of values, we connect them with a smooth curve in order to sketch the graph of an exponential function such as this. And it turns out that, for example, here is for our reference, this is our table. For example, whenever x is minus 3, for the 2 to the power of x, I have 1/8, that is this exponential function 2 to the power of x. When the value of x is minus 3, I have 1/8. 1/8 is very close to the x-axis itself, because 1/8 is somewhere over there, very close to the origin, and then it will be that point. If I choose minus 2, then I get 1/4. That is minus 2 and 1/4 is this point. 1/4 is also very close to the origin. And if I choose minus 1, now I get a half. That is this point. Now it is a little bit becoming higher than the x-axis. And if I choose 0, it becomes 1. If I choose 0, it becomes 1. And that is just the point over this point. This point is 0, 1. If I choose 1, it becomes 2. Now this 1 and the 2 are just this point. If I choose 2, that is 2 becomes 4. That is this point. And then we simply connect that pointers by a smooth curve, and that will become the graph of f of x is equal to 2 to the power of x. With a similar argument with the other functions, that is 4 to the power of x, 1 over 64. If I choose minus 3, that becomes 1 over 64. That is a little bit overlapping with this point, but it also lies here, but a little bit underneath that. And if I choose minus 2, then 1 over 16 is also this point, but below that. If I choose minus 1, that is 1/4 is over this point, but it is underneath the point. 0, 1, the same point here. For example, if I choose 1, that becomes 4. That is this point, and not that point, but this point. This point. That is for this function. We have to look at on this curve. If I choose 2, that is 16. That will be this point. 2 and 16. It will be that point. So when we directly connect those two pointers, for the left side of the origin, the pointers coming from both the upper functions, that is 2 to the power of x, and the lower one on our table, that is 4 to the power of x, are a little bit indistinguished. The two pointers seem to be overlapping. But on the right side, as the numbers increase, the two pointers are very much far away from each other. And the most important thing is that the graph of 4 to the power of x is passing underneath the graph of 2 to the power of x. So as the base increases around this point, the function is flattened. That is the graph of the exponential function. This problem is not the same as the previous problem, in the sense that in the previous problem we have plotted f of x is equal to 2 to the power of x, and say, for example, g of x is equal to 4 to the power of x, positive exponents. But in this case, as you can see, the exponents are minus, and the graph goes from left to right side, as you can see. And in order to plot the graph of a function such as this, for example, if I have minus 2, if I substitute into 2 to the power of f of x is equal to 2 to the power of minus x, I have minus 2 here, minus of minus 2 will be positive 2, 2 squared will be 4. I have minus 1 here, 2 to the power of minus 1 is 2, 2 to the power of 1, 2 to the power of 1 will be 2. If I substitute 0, 2 to the power of 0 is just 1. If I substitute 1, it becomes 2 to the power of minus 1, so it will be a half. 2 to the power of minus 1 is 1 over 2, that is a half. If I choose 2, 2 to the power of minus 2, 2 to the power of 1 over 2 to the power of 2, which is 1/4. Similarly, 3, 1 over 2 to the power of 3, which is 1/8. In a similar way, for 4 to the power of minus x, if I choose minus 2, 4 to the power of minus 2 is the same as 1 over 4 squared. As you all know, 4 squared is 16, so this is 1 over 16. If I choose minus 1, that is 4 to the power of minus 1, that is 1 over 4, 0. Any number to the power of 0 is 1. If I choose 1, it is same as 4 to the power of minus 1, that is simply 1/4. And if I choose 2, that is 4 to the power of minus 2, that is 1 over 4 squared. 1 over 4 squared, that is 1 over 16. So in this side, we have 4 to the power of a negative times negative, that is positive. For example, 4 to the power of minus 2 is 4 to the power of positive 2, that is 16, positive 16. But in this case, if I choose 2, that is 1 over 4 squared, that is 1 over 16. The argument is, and everything is the same as I have explained for the previous problem. And by joining the pointers from this table of values, you can simply plot the graph. The previous graph was going from this way, that is 4 to the power of x is going this way, and 2 to the power of positive x is going this way. But in this case, the graphs are going the other way because the powers are now negative. Now, I want you to focus on one very basic property of exponential and logarithmic functions, that is the one-to-one property of exponential and logarithmic functions. One procedure that we can test the one-to-oneness of this kind of functional property is what is called the horizontal line test. If no horizontal line intersects the graph of a function f at more than one point, if no horizontal line intersects the graph of f at more than one point, then that function is a one-to-one function. For example, if you have a graph like this kind of graph cannot be crossed by a horizontal line more than 2 times. For example, if I have this kind of horizontal line, no horizontal line is crossing this graph in more than 1 point. But instead, if I have, for example, something like a circle or an ellipse, the ellipse can be cut at 2 different points, at 1 point here and at another point there. The line can be cut. The line that is making the circle can be cut in more than 2 places. That is, if we distinguish that a given function is not crossed by a horizontal line more than one time, then that function is called a one-to-one function. So an exponential function is an example of a one-to-one function, in the sense that no horizontal line, no arbitrary horizontal line cuts the graph in more than one place. So what will happen if the function happens to be one-to-one? a function f is 1 to 1 when each value of the dependent variable corresponds to exactly one value of the independent variable. That is, if it obeys the horizontal line test, then a function has an inverse function. This is what I want you to recognize in this lesson. The point is that if no horizontal line crosses the given function in more than one point, it will be one-to-one function. If it is one-to-one function, the consequence of this is that it will have an inverse function. And the logarithmic and the exponential functions are inverse to each other. The inverse of logarithmic function is exponential function, and the inverse of logarithmic function is exponential, and the other way around also. So here is the consequence of the one-to-one property that will enable us to solve a problem such as 9 is equal to 3 to the power of x plus 1. How do we find the value of x such that 9 is equal to 3 to the power of x plus 1? In order to solve this problem, we have to use the one-to-one property which is associated with exponential functions. Namely, 9 is equal to 3 to the power of x plus 1, which implies that 9 can be written as 3 squared, which is equal to 3 to the power of x plus 1. So if exponential function is a one-to-one function, it means that every single point corresponds to a single value as a y also, as a functional value. So if 3 to the power of 2 is 3 to the power of x plus 1, it means that 2 must be equal to x plus 1, because there is a one-to-one relationship between the domain and the range of the exponential function. So 2 is equal to x plus 1. Then it turns out that this 1 can be subtracted from these 2, so x is equal to 1. We are able to solve this problem by closely understanding the behavior of the exponential function. That is the one-to-one property of the exponential function. It paved a way for us to be able to solve this problem. Let us see another example, b, which is a half to the power of x is equal to 2 cubed. In order to solve this problem, a half the power of x here is equal to 2 to the power of 3. And then my target is to find the value of x in such a way that when that x will be substituted into x, a half to the power of that x will be equal to 2 cubed. Again, by applying the properties that we have looked at a while ago, namely the one-to-one nature of exponential functions, what we are going to do is we write a half to the power of x, which is to the power of 3, which is our original problem, and a half means is 2 to the power of minus 1. So a half to the power of x means is 2 to the power of minus 1 to the power of x. And an exponential function a to the power of b to the power of c means is a to the power of b times c. So 2 to the power of minus 1 times x means 2 to the power of minus x. Then I can rewrite the term that is in the bracket here as 2 to the power of minus x, which is also equal to 2 to the power of 3. Then this minus x must be equal to, they are now having the same base, that is 2 here. So their exponent is minus x must be equal to 3. So x is equal to minus 3. That is the way we solve this kind of problem. Logarithmic functions and their graphs. So far we have been looking at exponential functions and their graph. This moment we pay our attention on logarithmic functions and their graphs. Logarithmic and exponential functions are one-to-one and they are inverses of each other. This inverse function is a logarithmic function. It means the inverse to the exponential function, such as this one, is just a logarithmic function. And the definition of logarithmic function with an arbitrary base a is for x greater than 0 and a greater than 0, and a is different from 1 for the very reasons that I told you earlier, that the base must not be equal to 1, because 1 to the power of any number is equal to 1, it becomes a constant function. So y is equal to logarithm of x to the base a. You read this one as y is equal to log x to the base a. You pronounce this one as y is equal to log, that is log of x to the base a, if and only if x is equal to a to the power of y. One property of logarithmic and exponential functions is that, for example, if I have a to the power of b is equal to c, it means that b is equal to log of c to the base a. If I have an exponential function which is written as a to the power of b is equal to c, b is log of c to the base a, and a is the b's root of c. So I have three variables, a, b, and c. If I want to find c, I will make a raised to b, which is c. If I want to find b, I will make b to be logarithm of c to the base a. If I want to find a, I will make a to be the b's root of c, like the third root of something or the fifth root of something or whatever. So that is basically the relationship between exponential and logarithmic functions. So the property that you see here is the direct consequence of that. Y is equal to logarithm of x to the base a if and only if x is equal to a to the power of y. If we originally have this logarithm, then a to the power of this b is equal to c. Means this a to the power of this y must be equal to x. Exactly coming from this property, we can write this one. The function f of x, which is log of x to the base a, you read this as log of x to base a or log of a of base x. I mean log of base a of the function x. F of x is a logarithmic function with base a. So the equations y is equal to logarithm of x to the base a and x is equal to a to the power of y are equivalent, and if, for example, 2 is logarithm of 9 to the base 3, it means that 3 squared is 9. 3 squared is 9. We have, for example, logarithm of 9 to the base 3 is equal to 2. 2 is logarithm of 9 to the base 3. Or we can write the base 3 to the power 2 is equal to 9, or equivalently I can write this 3 is equal to the second root of 9, which we always write as simply root of 9, which is equal to 3. That is the relationship between the three quantities. 2 is log of 9 to the base 3. 9 is 3 squared. 3 is root of 9. So that is the relationship that you should always remember. This is something I told you over here. Always you have to keep this formula in mind. So let us see the properties of logarithmic functions. The first property is that logarithm of 1 to the base a is always equal to 0. And the reason is a to the power. Always the base raised to the value here, a to the power of 0, must always give us the quantity here. That is 1. A to the power of 0 is equal to 1. If I write logarithm of a to the base a, it means that this base a raised to the result here, a to the power of 1, must be equal to a. And of course, as we can see, a to the power of 1 is a. And if I have logarithm of a to the power of x to the base a, it will give me x, because logarithm has a property that if I have logarithm of any number a to the power of x, that is an exponential a to the power of x, to the base, another base, which is also a, it means that logarithm of a to the power of x to the base a, I can rewrite this one as x times logarithm of a to the base itself. And any logarithm to the base itself, as we have seen it with the second property, is also equal to 1. So this is simply equal to x. So logarithm of a to the power of x to the base a is simply x. And this is because a to the power of logarithm of x to the base a is equal to x. This is directly coming from the property I showed you earlier. Probably I should repeat it somewhere over here. I said a to the power of b is equal to c, then b is equal to the logarithm of c to the base a. Then if I wanted to write this in that way, I can rewrite as logarithm of c to the base a. C is a to the power of b, so logarithm of a to the power of b to the base a, which is of course equal to b times log of a to the base a, which is b. And then you can write that as a to the power of log of x to the base a. If the base here and here are same, these two terms must also be the same. That is log of x to a to the power of log of x to the base a is always equal to x. You can simply substitute in order to show this is true. If log of x to the base a is equal to log of y to the base a, then x must be equal to y, in a very similar way as exponential functions. A while ago we were saying that, for example, if I have 9 to the power of some expression, say for example y, if I also have 3 to the power of some expression like 2x, then I can rewrite 9 as 3 to the power of 2y is equal to, say for example, 2 to the power of 2x. Then I have to first make the two bases equal in order to take the exponents to be equal to each other. Otherwise, if this has a base 3 and this has base 2, then I cannot take this 2y to be equal to 2x. Because in order to equate the exponents to each other in a similar way that we did before, for example, we have 3 to the power of 2, we have 3 to the power of x plus 1. Then, because the bases are the same, 3, 3, then we took 2 equal to x plus 1. 2 is equal to x plus 1. Then from that one, we already got x to be equal to 1. The bases must be the same in order for us to equate the exponents. In a similar way for logarithms, the bases must be the same, that is to the base a, here also to the base a, so that we can say x is equal to y. That is the point. Use logarithmic properties to simplify. Logarithm of 1 to the base 4. Here are the answers, and the answers are already given here, but we have to verify that logarithm of 1 to the base 4 is equal to 0. That is logarithm to any base with the properties that we saw before. That is with this property, logarithm of 1 to any base is always 0. Because of that, logarithm of 1 to any base is 0. That's why logarithm of 1 to the base 4 has to be 0. Here is logarithm of root 7 to the base root 7. Logarithm of any number to its own base is equal to 1. Because of this property, logarithm of root 7 to the base root 7 is 1. In general, logarithm of any number to the base itself is equal to 1, provided that that specific number is within the domain of logarithms. Here, if I have 6 to the power of log of 20 to the base 6, if we have 6 here, then the answer must be 20 there. In general, a to the power of logarithm of x to the base a is always equal to x. And you can easily verify this relationship from the exponential relationship that I told you before. A to the power of logarithm of x to the base a is x. Always you look at the a here, same, then the answer must be the x here. This brings us to the end of this lesson. Thank you very much. See you with the next lesson.